Okay, so the most up-to-date theory of acids and bases is Bronsted-Lowry. So although it's still true, acids have hydrogen, bases have hydroxide, it didn't fully explain all of the acids and bases that exist. So for example, right, NH3 was the one I'd mentioned before. So ammonia does not have a hydroxide, and yet it does have a pH higher than 7, which means that it's creating a base. So this modern theory of acids and bases is more all-encompassing for the different types of acids and bases you're going to come across. So an acid is now defined by a substance or species, so it could be an ion, it does not have to be a molecule, that donates or gives away a hydrogen ion. Okay, so hydrogen ion can also be referred to as a proton, because really a hydrogen atom has one electron and one proton. So when that one electron is gone to become an ion, really all that's remaining is one proton. So the term is interchangeable. A base is now a substance or species, again, it can be an ion, that will accept a hydrogen ion or a proton. So what ends up happening is you have one substance that's losing a hydrogen ion and one that is gaining it. And to be honest, it won't really make a ton of sense until you see some reactions written out. Okay, so all of these acid-base equilibriums we're going to be looking at are in fact equilibriums when you see the double arrow, of course. But when you have a acid-base pairing, we call that a conjugate acid-base pair. So that doesn't make a whole lot of sense right now, but let's look at this example. So here we have a base reacting with an acid. So you're probably thinking to yourself, well, this is water. How is this a base? So let me use a different example actually to start, just because something you're a little bit more familiar with, okay? So let's say I had hydrochloric acid reacting with sodium hydroxide, okay? So when we have this reaction happening, the hydrogen is being lost from this HCl molecule. So technically, this is now defined as being an acid because it is giving away a hydrogen ion. And because the NaOH is now going to be accepting it, we call that now a base because of the accepting. So it's not because of the hydroxide that's there. It's because of it taking that hydrogen ion to form water, right? So the remaining compounds, right, are just a result of that giving and taking. And of course, the focus is the hydrogen ion. Technically, this is taking the sodium ion, but the focus is where is the location of the hydrogen moving to and from. Okay, so water, in this case, let's say we had an acid, hydrofluoric acid reacting with water. So this is something that is going to happen. You can have an acid that is essentially reacting with water or a base that is reacting with water. So when these ions are in solution, you actually have other species that are made. So the acid, right? So an acid is always something that will donate a proton or donate a hydrogen ion. The other substance is the one that's taking it. So there's always a give and take. Once you know which one is gaining or losing, you can figure out what the other one is because it's the opposite. So here we would have fluorine ions, and now what happens when you have water with the additional hydrogen, we're making a new polyatomic ion. So this is called a hydronium ion, and it is a polyatomic ion. It should be on your chart in the orange booklet. So this hydronium ion is going to come up again much more frequently in this chapter and the following chapter. However, for now, Like the goal of today is really identifying what's an acid, what's a base. Okay, so let's say we were to take this second reaction I wrote out and go backwards, right? Because this one is an equilibrium process. So you have to imagine for it to go in the reverse, the hydronium ion would then donate back the hydrogen ion to the fluorine, so that way it can make HF again, right? So in this case, on the product side, the one that's doing the giving away is the H3O+. So that's defined as our acid on the product side. The fluorine ion is accepting that hydrogen ion, so it is a base. So wherever that hydrogen is being lost, that is an acid. The acceptance is the base. So the term conjugate, things that are on the conjugate, it'd be helpful if I could spell that. So the term conjugate is actually in reference to the product side of the reaction. So when we say that, they mention this up here, the conjugate acid-base pairings, what they're looking at here is the before and after. So before the hydrogen was lost and after the hydrogen was lost. So I'll give you an example. HF would be paired with F. So this is like before the reaction. This is after the forward reaction happens. So the conjugate, so technically fluorine would be like a conjugate base. Hydronium is a conjugate acid. But the pairing would be HF and F. The other matchup that would happen is before and after with water. So we have H2O and H3O+, which would be another conjugate acid-base pair. Right? If we look up here, the base is the hydrogen giver. So in this particular case, so NH3 is just one of those weak bases that you are expected to know is a base. Okay, so I'm telling you now, right? So whenever you see NH3, that is definitely a base. So you know that the hydrogen ion is going to move from the water to the NH3. So if you look at the product side, this makes sense. Remember that water, when it splits, it's technically HOH. So when that hydrogen is lost, the remainder of what's left over from that water is a hydroxide ion. What you're making with this NH3 is now the ammonium ion, right? The polyatomic ion. And if you look at the pairings, right, if this were to go in reverse, right, the proton would move in the opposite way. So the blue blocks here, right, these blue lines is showing you the conjugate acid-base pairings. Right, so if we take a look here, we have to identify, label the acids and bases for the reverse and forward reactions. Right, so this is going to be pretty easy to tell because you're going to track, well, what's going on the product side, right? So here, this is like a very straightforward because it's the only one that has hydrogen. So we know this is going to be our acid. This is going to be my base. If this were to go in the reverse, right, the hydrogen is going to go back onto the IO3. So this would be my acid. This would be my base, right? For part B, right, and pause at any time, give them a try, and then continue watching the video so you can see how you did. But here we have HF, which is an acid, right? That's hydrofluoric acid. So the hydrogen is going to move on to our HC2O4 -1. You can see it on the product side, what's going on here as well, right? So this is our acid, this is our base, this is our acid, this is our base. Over here, we have an aluminum water hydrate complex. But if you look at the product side, it can tell you what's happening, right? So we went from SO3 to HSO3. So we know that the hydrogen went on to the SO3. So this is our acid, this is our base. And of course, to go into the reverse, this is our acid and this is our base. Okay, so if you were to, you didn't have to here, but if you were to label the conjugate acid-base pairings, right, you would match them up with the before and after. And you'll notice it's always the opposite. If it's a base on one side, it'll be an acid on the other side. So HiO3 to IO3, right? HF with F, right? So you would just match up the befores and afters. You didn't have to for this question, but just to kind of get into the habit of doing that. All right, so conjugate acid, conjugate base. So this is now you have to look at essentially this is like the before and after of your acid base. So acid would be essentially everything that's here is going to be donating a proton. Everything that's on the base side is going to be after it's accepted it, right? So conjugate acid is H2O2. So afterwards, this should have one less hydrogen, okay? In terms of charges, remember that hydrogen ions have a positive one charge. So when it's being lost, you have to recognize that it's taking with it that +1. So it went from something that is neutral to something that is -1, right? So if we look at the second one here, it has a -1 charge. So that means when it has the hydrogen back on, it should actually be neutral. Here we have HCOOH. So here we're going to lose that hydrogen, and we should have a -1 charge. Here we have a -3 charge, so that means over here our charge should actually be -2, right? So it has an additional hydrogen on it. Because remember, if we're looking at the base side, that means that we're looking at it after it's already lost that hydrogen. So you're kind of working backwards, well, forward and backwards, depending on what's given here. Okay, so here we have to complete the equilibria. So you have to write the products out, label the acids and bases for forward and reverse, and circle one conjugate acid-base pair in each equilibria. Okay, so you can pause this video and give this a try. There's 3 here, I believe, and see how you do. Okay, so here we have, right, we know this is a base. Here's our acid. So we're going to have NH4 plus NO2 -1. I'm just going to write the products out first. So here we have, right, one of the hydrogens that's going to come on to form HCN. This is going to be H2. Remember, the order of what you're writing doesn't matter, right? If I put HCN second instead of first, it's the same thing, right? Just depends. It just has to be on the correct side of the reaction. For C, right, our hydrogen is moving over, so this is going to be HPO4. This should be -2 plus HS -1. Okay, so in terms of if this were to go backwards, right, you have to label accordingly. So this is acid, base, and then here if we were to go to reverse, acid, base. Okay, in terms of pairings, right? So you know you'd have to match up. It's asking you just to circle one. Really just make sure you are matching up with the correct, whichever one you're choosing, right? Make sure you're choosing the one that matches with the after. Okay, so amphiprotic species are things that have the ability of either gaining or losing a hydrogen ion. So we actually already saw this with water. So here's an example, right? When water is with a base, right, so we know NH3 is a weak base, it will behave like an acid. When water is with an acid, we know the hydrofluoric acid is an acid, right? It will behave like a base. So amphiprotic, amphi means that it can do either or, right? So how you know what it will behave like depends on what it is with. So for example, HS is another one. If you put this with an acid, it will behave like a base. If you put this with a base, right, it has the ability to act like an acid, right? So it depends. Because it has a hydrogen, it can lose it. And because it has this charge here, it can also gain it, right? So these species, you're going to come across them. Whatever they are matched with, it will behave as the opposite.